Welcome back my dear friends, very good morning, good afternoon and good evening to all of you, and this is the DADM, which is data analysis and decision making 1, this NPTEL MOOC series course, and this total course if you know, which I do mention in the beginning of each class in general, and then I basically wrap up whatever we have considered in the last class. So, this is a 12-week course for 30 hours, and each week we have 5 lectures, each lecture being for half an hour, and we are in the 15th lecture. That means, we are going to end our 3rd week lecture series. So, if you remember, and my name is Raghunandan Sengupta from the IME department, IIT Kanpur. If you remember, we did discuss in the last 2 lectures, which was the 13th and 14th, a little bit detailed, because these will be coming up time and again later on, about the chi-square distribution, about the t distribution, about the f distribution. For the chi-square distribution, it was basically chi-square was being formed by the sum of the squares of n number of standard normal deviate, and we also saw that chi-square distribution could be of degrees freedom of n and degrees of freedom n minus 1. Now, for n, we can have the degrees of freedom provided that the set of information is not being lost for one case. What is that case? I am going to come to that later on, I will just repeat it. And for degrees of freedom n minus 1, we have lost 1 degrees of freedom, based on that we will proceed. Let me tell you another thing, obviously I did not mention that, but it will be coming up later on also. I will basically wrap up these 4 or 5 important points about all the 3 distributions at one go, once I basically give the wrap up of the revise what we considered in the 13th and the 14th lecture. Then we went to the t distribution. T distribution was being formed by the ratio of a z divided by the square root of a chi-square divided by its degrees of freedom. So, I am just mentioning it because they were being utilized, this concept of sum of the squares or division, all these things would come later on. Then for the t distribution also, we had a t distribution with n degrees of freedom, t distribution with n minus 1 degrees of freedom. And I did mention that time and again that the t distribution has, in the long run, if the sample size basically becomes very large, that means degrees of freedom becomes very large, then the mean value and the standard deviation value becomes exactly equal to 0 and 1, which is basically the case for the z distribution also. So, t distribution can mimic the z distribution, or the other way around. That means, in case if you have a t distribution with larger degrees of freedom, we can safely use the z distribution in place of t distribution and continue with our work. For the tables, I will come to the tables later on also, even though I only discussed the tables for the z distribution. Then later on we came to the f distribution. So, in the f distribution, you are comparing 2 populations with the corresponding sample size being m as in mango, n as in Nagpur, and we considered the f distributions with m comma n degrees of freedom or m minus 1 n minus 1 degrees of freedom, depending on what the loss of information is. Now, remember one thing, we also did mention, and I also did harp on the point, that there are 2 s. S is basically the standard error for the sample, which is basically the square root of the sample variance. So, in the standard error, you basically have s dash square and s without the dash square. So, the s dash was the case where you do not lose any degrees of freedom, the mean value of the population remains as mu, and we divide by n in order to basically find out what is the square of the standard error for the sample. Now, when we are losing 1 degrees of freedom, that means the population mean value mu is not known, we replace it by the sample mean, which is x bar n, and then we divide it by n minus 1. So, we lose 1 degrees of freedom because you are utilizing the first set of observations for the first time x 1 to x n to find out the best estimate for the population mean, which this is the sample mean. And then we also showed that how the different ratios, that means, if you remember that I did mention that how the z chi-square distribution was formed, how the t distribution was formed, and the f distribution was formed by chi-square divided by its degrees of freedom in the numerator, and in the denominator another chi-square with its degrees of freedom. So, these 3 ideas of the ratios and how the formation of these 3 distributions were formed basically helps us in trying to understand what are the different rules based on which you can utilize these 3 distributions. Now, one thing which I would like to mention here before we proceed further on, and later on we will see that in the case of interval estimation, point estimation, and especially in the case of hypothesis testing, this would be very important, that remember this chi-square distribution is used for the case when we have something to do with the variance of a population and you want to test it. The Z distribution, so that means only one population, we want to basically, we have some information from the past, we want to basically verify if that fact is true or not. Now, the F distribution is used for the case when we have something to do with the comparison of the 2 sample means variances, sorry, 2 sample variances or the standard deviation of the population, such that we use the chi-square with m comma n or m minus 1 n minus 1 depending on the case as it is. Now, the question would obviously arise that when we do use the Z distribution and the T distribution. So, as you can guess, the Z distribution, the T distribution would be used in order to find out something related to the mean of the population, Z being the case when the information set related to the standard deviation is known, and T being the distribution when the standard deviation information, that means for the population, is not known. And when you want to find out the differences of 2 means also, then you use either the Z or the T as the case may be. So, this last few minutes or the last few seconds which I mentioned about when Z and T would be used and when chi and F would be used, I would repeat that time and again. So, please be rest assured that these things will become very clear to you as you proceed and discuss the ideas. Now, we will consider, I am just giving an example, I will come to the details later on, most probably in the 16th, 17th lecture. So, when if you remember, we also discussed that if you have a population, so your basic idea was to find out the parameters. So, parameters for the normal was mu and sigma square, probability was for the binomial were n and p, exponential was lambda or a and lambda, Poisson was lambda or theta, whichever you express. And using these parameters, location, shape and scale, which generally in general statistics sense, the location, shape and scale are given by alpha, beta, gamma in order to express that what we mean by the location, shape and scale parameter. So, using this location, shape and scale parameter, we find out the first moment, second moment or the combination of the moments, first moment being mean value, second moment be the variance and so on and so forth. Now, if we know about the population moments or population parameters, then trying to find out the parametric distribution of the sample becomes easier. In case if the population mean values, population variances of the moments of the populations are not known, what we do is that we replace by the characteristics from the sample, which is, if you remember, is small t suffix n. So, this t is nothing to do with the t distribution, remember that. The small t suffix n is basically the characteristics of the sample which mimics the population parameter or population characteristic to the best possible extent. And we did also mention that the 2 important properties being unbiasedness and consistency, and if you remember, I drew that diagram with a graph for corresponding to the normal distribution in order to basically portray that what we mean by unbiasedness and consistency. So, generally considering the properties of unbiasedness and consistency, we would basically have the estimators for different type of distribution. I will assume without the proofs what are the estimators. I am not going to go into the details of unbiasedness and consistency. Maybe many of the cases the consistency property may not hold, but we will try to utilize those estimators in order to basically give a feel that how they can be utilized. Now consider this case, and this is very heavily used in the case of extreme value distribution, even though extreme value distribution discussion is not part of this course. Now, in extreme value distributions or if they are skewed value distributions, say for example, you want to do this experiment, and before I start the experimentation, let me give you the background, and what is written on the slide would make sense, and then you will understand that what I was going to say. Consider that you have a discrete distribution actually from the population, and the minimum and the maximum values are a and b, and now a and b are not known to you. Now, I would ask you the question that how can you find out a and b? Is it possible? So, there would be different ways how you can basically come out, but let me give you a very simple example. Say for example, you pick up a sample from that uniform discrete case. The first case of n observations, you pick it up, note down the minimum and keep it. Again, and you either replace this observation into the box or you do not replace. So, that would hardly matter, because you are considering that the whole population is infinite when you are picking up observations samples of n number in size. You do the second time, pick up the mean from that second set of observations 1 to n, note it down and keep it aside. You continue doing it. So, now what you have is basically for each case you have a sample where you have noted down the mean, and if you continue doing it, technically it is possible that at one case when you do it infinite number of times, that the minimum of the minimum would basically be the best so called best predictor. The word best I am using not in the sense of unbiasedness, not in the sense of consistency, which is basically from a very layman's point of view how you can understand. So, that minimum of the minimum would be the best predictor for A, and if you do the same thing for the maximum, then the maximum of the maximum would basically give you the best predictor for B. So, and based on that we can basically continue the work. So, this is basically what it says in point number 1, if x is the uniform discrete with A and B, then A hat, and now the hat is being utilized to basically denote that what is the estimator from the sample and how it is able to basically give us the best prediction about the population. So, A hat would be the minimum from x1 to xn, and if I continue doing it, I will find out minimum, many minimums, and then I find out the minimum of the minimum and continue. While B hat, which is the best predictor of B, would be the maximum from x1 to xn, and again as I said, you will continue taking the maximum, many maximums, find out the maximum and basically continue. So, these technically, and what I am going to discuss would be basically with the many of the estimates from the sample, which are the best predictors for the population parameters based on which you can do the experiment. That means, based experiment in the sense that we pick up the sample estimate, which are the best predictors for the population parameters, and use this sample estimate to basically do our experiment or do our studies, whatever it is. For the binomial distribution x with the parameters n and p, then if I want to find out p hat, which is the probability of success, or q hat, which is the probability of failures, and if you remember that 1 is equal to p plus q, then p hat would basically be the number of things which are favorable divided by n, which is the set of observations which you are picking up. So, say for example, if you want to find out an experiment or want to find out what are the number of red balls and or what are the number of white balls in a box which has red and white only. So, we will pick up observation, find out the number of reds, divide by the number of observations you picked up, and basically try to estimate what is the probability of finding out the red ball. Similarly, we will do for the white balls also. Now, consider we have a Poisson distribution, again without proofs, all these things which I am saying without proofs. So, for the Poisson distribution, the best, if you remember, the lambda is the mean value, so, and it can be proved mathematically the best estimate for the lambda, which is the mean of the population, is the mean of sample mean. So, hence if I pick up observations 1 to n, add them up, divide by n, that will give me the best estimate for lambda. Hence, it is given as lambda hat is equal to x bar n. So, this is done. Okay. Let me come to the exponential case for the continuous case. So, few are the estimators for the continuous case. Pay very special attention to for the normal case, other things would be discussed as and when we proceed. Consider the normal distribution, mu and sigma square are the parameters we need to find, then the best estimators for the sample for the population mean mu would basically be the sample mean, which is x bar n. Now, the question would arise what is the best estimator for the case when we have want to find out something to the variance, to do with the variance of the population, which is the normal distribution. So, in this case there would be two outcomes, and if I have mentioned that in the 14th class or 14th lecture. So, consider the population mean is not known. So, in that case you will use, if you remember, I did mention about S dash and the S without the dash. So, consider the population mean, let me start from the easiest one. Consider the population mean is known. So, in that case the population variance, if it is not known, we want to find it out, then the best estimate from sample would be 1 by n summation of x I minus mu whole square. That means, we are trying to find out the difference between the set of observations from the population mean, square them up and add them up and divide by n. But in this case, you should remember that we are dividing by n because we are not losing one set of information, considering the sample set of observations had been picked up. Now, this would basically be the S dash. Now, when we do not have the population mean, so hence you want to replace the population mean by the best estimate from the sample. In that case, the best estimate from the sample, which will mimic the population mean, which is mu to the best possible extent, would basically be the sample mean. So, if you are replacing mu by x bar n, in that case you have utilized the first set of observations from x 1 to x n the first time and tried to find out the sample mean. Hence, the degrees of freedom would be lost by 1. Hence, the value now would be S dash would be summation of x I minus x bar n whole square, sum them up, divide by n minus 1. So, this is what is given. In case if you have, say for example, and this will be utilized time and again, please bear with me. In case we have basically the exponential distribution with only one parameter, which is lambda or theta, that means the a value is 0. In that case, we will try to utilize the actual sample mean to be the best estimate for the population mean and proceed accordingly. Hence, lambda hat or theta hat would be given by x bar n. Now, somebody may be thinking that what if f a is given? Is it not possible that we pick up observations, find out the mean and then continue with the work? So, obviously, those type of layman ways of trying to handle them are intuitive and they may give us results, but theoretically the results may not be sufficient to prove about the property of unbiasedness and consistency. So, I will give you the results as we proceed and try to utilize them as and when the case arises for our studies. So, let us consider an example. It was found that the respective number of members in 10 different families are respectively as 4, 5, 6, 7, 8, 3 and so on and so forth. So, if you consider that the number of members in a family to be uniformly distributed, then the estimated value of A, that means A would be what? In this case, that we will find out the minimum of all the set of observations, which is basically 3, and the maximum of that set of observations which will give us B. That means A hat and B hat would be the best predictors of A and B, would corresponding the values be 3 for A, which is A hat, and 8 for B, which is B hat. Now, consider you are testing the components coming out of the shop floor and find out that 9 out of the 30 components failed. Then the estimated value of P, which is the proportions of the objects which are bad or good, whatever we say, they would be given by 9 by 30. So, say for example, that if you find out that 9 of them fail, which means the number of objects, that actual proportions of the probability of that total lot to have defective and non-defective one would be in the following way calculated. So, the probability of the defective one would be 9 by 30, because 9 are the bad ones out of the 30 pickings we are doing that, and a corresponding value of P, which is the good items, would be, in the case if the actual value of Q was given, it will be 1 minus Q would give us P. In this case, as Q has been replaced by Q hat, which is the best estimate, you will find out 1 minus 9 by 30, which will be 21 by 30, will give us the best value of P, which is P hat. Let us consider the next example. At a particular tailor machine in one of the bank branches, it was found that the number of customers arriving in an unit time span were given by 4, 6, 7, 4, 3, 5, 6 and 5. So, they are arriving, and obviously, you want to find out the rate would be given by the mean value and what is the expected value based on which you want to do the calculation. So, this for a Poisson process is the best estimate for the population mean would be the sample mean. So, to find out the sample mean, what we do, we add the set of observations divided by the number of observations, that value of lambda hat or mu hat or theta hat, whatever you are saying, would be given by 5. Suppose it is known, next example, suppose it is known that the survival time of a particular type of bulb has the exponential distribution, you test 10 of them. So, n sample size is 10 and the bulbs were found to be have a survival time of 150, 225, 275, 395, 155, 325, 75, 20 and 400 hours. But remember here that in this case, very intuitively and rightly so, we are considering A is to be 0, because if you put on the bulb and it can fail immediately. So, obviously, in that case A is 0. Then the best estimate would be, as I have already discussed, for lambda would be lambda hat is basically given by the sample mean. So, for the sample mean what we do, you add up all the values starting from 150 to 400, divide by 10, and that value comes out to be 202. Okay. Now, before we are going into, I am giving the flavor and then I will switch over to the concept of estimation and all these things. Now, whenever we want to do some studies, and I will give you this background using the multiple linear regression. Whenever you do some studies, our main idea is to basically to find out an estimate from the for the population values and do those studies in such a way that they mimic the population characteristics to the best possible extent. And for that I gave you the ideas of consistency, ideas of unbiasedness, and proceeded accordingly. Now, the task is, there are three type of things we will try to cover in the univariate case and the multivariate case. The first one being the case when you want to find out the actual point value of that particular population parameter, point 1. Another would be basically you want to find out the interval range between which the population parameter would basically be, point number 2. And point number 3 would be the case when you want to basically hypothesize or basically pass the judgment based on some set of information which you have, and you want to either disprove or prove depending on whatever set of observations which you have and what is your conclusion based on those set of observation on which you do the statistical test. Now, for the case of the point estimation, our main task is to find out unbiasedness, consistency of those sample estimates which I just discussed, like that for the case for the lambda, for the case for say for example, for the Poisson distribution theta or lambda, for the case for the normal distribution is mu and sigma. So, obviously, we replace them by their hat values corresponding to what the information we get from the sample. Now, what is important for us further on is to find out that obviously, when we want to basically predict or estimate the population parameter, we would also be interested to give the idea that what is the interval between which it will lie. So, when we are trying to basically do that, so our main task would be to what level of significance we are able to meet. So, level of significance means that what is the accuracy level, consider it very significant, very simply. Now, when you are mentioning the point of level of accuracy or level of significance, what we will, or level of confidence, what we mean is that if my level of confidence is 90%, what I want to portray is that if I keep doing this experiment 100 number of times, 90 of these times are successful based on the fact which you have produced, and 10% of the cases the case is not successful. Hence, the probability of success or the level of confidence is given by 90 by 100, which is 0.9, and in the case of not being successful will be given by 10 by 100, which will be 0.1. Now, one thing should be remembered, that whenever you are trying to basically understand the level of significance or level of confidence, there would be technically 3 ways. 3 ways are not distinct ways, but I am giving you a flavor that 3 ways of trying to analyze the problem. In one case, it can be of the type greater than whatever value we have, and based on that the interval or the hypothesis would be framed accordingly. I will come to the exact things of hypothesis and interval later on. And in the second case, it would be basically either less than type. So, given one value we want to basically hypothesize or basically pass in judgment that it will be less than type, and in the third case it will be within the certain range. So, when we basically mean the level of confidence or say for example 90%, 10%, whatever it is, we will frame the question in such a way that the total probability will be divided accordingly. So, let us remember that. So, when I am using the word that the mean value of the say for example, some tie rods which are coming up from the shop floor is say for example 1.2 meters, and if I am hypothesizing that on an average the values are greater than, then obviously it would mean that the greater than type would have a certain probability depending on my level of significance or level of confidence. When I am mentioning the point that they would be less than 1.2, then obviously the corresponding level of confidence would be framed accordingly. When I am saying that they would be somewhere between 1.2 and say for example 1.25, in that case that interval would basically determine and give me some information what is the level of confidence which you want to have. Now, in all these cases what we will consider technically is that whatever the distribution is, it is a binomial distribution, it is basically a Poisson distribution, if it is an exponential distribution, hypergeometric distribution, obviously our life would be best if we knew the exact values of the sample estimate and proceeded accordingly. But the problem is that in many of the cases trying to find out the exact values of the parameters for the population given the samples estimates is not possible. So, what we do is that we consider the central limit theorem to be true. So, if you remember that it did mention about the central limit theorem, and that will now become very important as we are discussing. The central limit theorem to be true, we will utilize the central limit theorem, replace the actual distribution by the normal distribution, but be rest assured the corresponding mean value and the sample and the standard deviation or the variance of that particular normal distribution would be some property of the norm of the mean value and the standard deviation of the actual distribution. So, when we are taking a binomial distribution, then the corresponding central limit theorem will give us a normal distribution, where the mean value and the standard deviation or the variance of the normal distribution would have something to do with NP and NPQ, where if you remember NP and NPQ are the corresponding mean values and the variances of the binomial distribution. So, we will consider those things in such a way such that trying to solve the problems would be easier. Now, remember on one thing, that the case of whatever we will be discussing, the interval estimation, the point estimation, the hypothesis testing would be given from the viewpoint of the univariate case, and later on it will be given in such a way that you can easily consider the multivariate case very simply. This has been more of, at least in this 15th lecture, I have been discussing more about the concepts we are going to come across, and I will come to this actual utilization of the theorems and utilization. Remember me, I am not going to discuss the theorems in details, the utilization of the theorem, the concepts through diagrams and through 3 simple problems. So, if you read those type of books which I have suggested, it will be it will give you a lot of informations about how we are going to analyze the problems. The reason being that for when you are trying to basically analyze the problems from the point of view of the multivariate cases, many of the cases may become a little bit complicated. I am not saying they are absolutely difficult, they may become complicated, but the idea of trying to basically understand the multivariate distribution with the case of the univariate case would give you a lot of confidence if you are able to handle the simple problems in the univariate case. With this, I will end this 15th lecture, and the slide which is in front of you, I will come to this, please bear with me, I will come to these discussions later on. So, with this I will end this lecture, and thank you very much for your attention, and have a nice day. Thank you.